Okay, the seems ready to continue. Where I stopped, I was showing some power spectrum data. So the important question to talk about is how we establish the precision of those measurements, because we can't get any cosmological inferences unless we know what the error bars are. So this is the subject of cosmic variance, which really is a shorthand for saying how would the results have been different if we produced a different realization of the statistical process that makes the cosmic density fluctuations. And we can analyze this quite easily on large scales on the assumption that the density field is Gaussian. So let's think how this goes. We're making a density fluctuation. It's in the real, well, so when we make a complex Fourier amplitude, we're effectively adding up the density field from many points. And the density field itself has a Gaussian character, so that means any sums of Gaussians is also a Gaussian field. So that tells us that both the real and the imaginary parts of the Fourier coefficient separately have Gaussian distributions. So that's easy to show. That means the probability on the real and imaginary part of delta, the Argand diagram, is circularly symmetric, and it factorizes into a function of radius. So the power distribution is exponential. The probability of exceeding the power exceeding a given value x is just e to the minus x divided by the mean power. So that means that power spectra are by their nature very spiky. It means if you actually resolve power into individual modes, you'll see a substantial scatter in the values of the power. And what you have to do is average over some range of k in order to measure the precise power to a precision that's set by the number of modes that you're averaging over. So basically, the fractional error in the power is just 1 over the square root of the number of modes in the k range available. And I've specifically broken the power into the total, that is the power that you're interested in of the cosmic fluctuations and the shot noise, just a discreteness correction. So imagine that we had a survey in 2 parts, similar volumes, but different number densities within those volumes. So they'll have different shot noises. Therefore, if you want to measure the power optimally over those 2 parts of the survey, as always with any statistical process, if you have 2 independent measurements, you combine them with a weighting that's inversely proportional to the variance. So that variance has to go since the number of modes is the same in each case, it's just a question of the relative size of the shot noise to the power. So you should weight the power from those 2 volumes by 1 over 1 plus p shot on physical power. And since the shot noise is just 1 over the number density of the galaxies, you have this factor 1 over 1 plus np all squared. And that's equivalent to weighting the density field in each of these subvolumes by the square root of that factor, 1 over 1 plus 1 over np. Or a simpler way of thinking about it is that you construct a density field by weighting the galaxies within the survey according to the density. That is, you need another factor of n to convert from delta to the number of galaxies that you have, and then you have just 1 over 1 plus np. And so this is a thing deduced by Feldman et al. In 1994, and it's a very nice expression because it does the right thing intuitively. If the number density is extremely high, what this says is that galaxies are down-weighted. So effectively, you're weighting each volume equally. This factor would become unimportant in the volume weight. On the other hand, if the number density is very low, this factor goes away and you weight each galaxy equally. So you naturally transition between removing areas of the survey that are dominated by shot noise in a smooth way. So this is now routinely used to do power spectrum estimation. The nice thing about this formula, though, is that you can ask a question, which is, supposing I have a finite observational resource, a certain amount of time on a telescope, and I've got a choice of either surveying at a high galaxy density over a small area of sky or being dilute over a large area of sky. Well, the volume goes as the reciprocal of the number density that you choose for a fixed survey time, fixed number of galaxies. And so the number of modes goes as 1 over the number density. So you have that dependence on the number density here, as well as the dependence from the FKP weight. And it's easy to show that if you choose NP of exactly 1, then you get the highest precision in the measurement of the physical power for a fixed survey time. So it's natural today to choose relatively dilute surveys of the universe, assuming that you have some idea, as we do now, of what the target level of power is. So that motivated the great success of the Sloan, which was to go from the fully sampled surveys of something like the 2DF that I showed you at the start, and put the observational effort to the same number of redshifts into a larger volume. So this is this picture is marginally dominated by shot noise, but for large-scale structural statistics, it's much more powerful than the same number of redshifts concentrated in a smaller volume. All right, but cosmic variance isn't all powerful, so I should just say a few words about ways in which it might be evaded. You see, the thing is that if you have, imagine if you have 2 different populations of galaxy. They know about, so the mass is fluctuating. You might have 2 kinds of galaxies. Let's say you split them by color. That's easy to do. Ellipticals and star-forming galaxies are readily distinguished, and they'll have different degrees of bias, but they'll trace the same matter fluctuation. Actually, I've done it the wrong way around. Red galaxies will have high bias. It doesn't matter. The point is, if the bias is different, and you can measure that in a way that's independent of cosmic variance. So, based on our previous discussion, you might have said that the relative bias of 2 populations would be the square root of the autocorrelations. But each of these autocorrelations are subject to cosmic variance. So you might think that this bias ratio would be an uncertain element, but in fact, even you can see mode by mode, the bias ratio is just exactly the mode amplitude ratio. There's a similar discussion to be had in redshift space, but I'll talk about redshift space tomorrow. This sounded very good when it was first proposed. The problem is, though, that you need 2 tracers that are different in bias, and also are not shot noise dominated, because basically this method of cancelling out cosmic variance only works if cosmic variance dominates over the kind of grainy noise from shot noise, which isn't in common to the 2 populations. So this diagram shows that if you have a signal to noise of about 100, that is, say, the shot noise correction to the power is only like 1%, then you can get factors of several improvement in the error bars on cosmological parameters. But in practice, it's very hard to get out into this regime. So cosmic variance, for most purposes, is still the main limit, even though in principle there should be ways around it. All right, let's move on then from having discussed what we can do in the limit of large scales with linear bias applies to the real world. And I've emphasized that cosmic variance wants us to increase the number of modes that we can sample. And we can do that in two ways. We can either increase the survey volume, but we can also go to larger wave number, because the number of modes increases as the cube of your maximum k. So there's a nasty trade-off to make. You want to move to higher k for greater statistical precision, but at higher k things are nonlinear, and so you need a more complicated theory. You also need a better projector. But there is some high redshift large-scale structure in this n-body slice, which I hope will become a bit more apparent as the universe evolves. Yes, okay. So this is just to emphasize that nonlinear evolution basically makes the universe filamentary, which I guess even on this terrible picture you can see. And that development of the cosmic web manifests itself in the power spectrum. So here's the plot of how the power spectrum would evolve, ranging from redshift 0 at the top, redshift 4 at the bottom. So pure linear theory is the solid line. These are the transfer functions so carefully calculated by Dimitri. But what we'd actually get are these dashed lines. These look like analytic formulae, but they're not. They're a fitting formula as a package a student of mine developed a few years ago called HaloFit that's widely used. It's basically just a physically motivated fit to n-body data. So you can regard this as just what n-body simulations do. So you can see at wave numbers of... Hello? Yeah. This seems to be coming and going. 0.2 or 0.3, the nonlinear corrections to the power are substantial. You might think that that would be useful because it would allow you to learn something about the overall amplitude of mass fluctuations, because you could take this high redshift spectrum and might be considered as a candidate for low redshift clustering with a lower value for normalization, sigma 8, and you could tell the difference by the nonlinear corrections. But the problem is that I showed you earlier on that bias can depend on scale, certainly when the correlations become nonlinear. So you couldn't tell necessarily, given galaxy data, that you weren't looking at some nonlinear phenomenon in the bias. But there is a way to actually split this degeneracy by using higher order correlations. And just let me say a few words about those. In the same way as you can have a 2-point correlator that just tells you the probability of finding a pair and 2 volume elements with some separation, you can have a triplet or any n tuple. And the probability of having one object in each of a number of little boxes is just the nth power of the mean density times the product of the volume elements times something that represents the degree of correlation. And that general n-point correlator just has to be the ensemble average of the products of all the 1 plus deltas. So you expand that out, and there'll be sets of terms in the different n-point functions. So at order 2, we just have the 2-point function. At order 3, we have 3 2-point functions for each of the separations of the pairs out of the triplet, plus a genuine reduced 3-point function. And just as with the 2-point function, there's a k-space analog. You can express this quantity zeta as a Fourier transform, and that gives you the bispectrum. So I showed you before the 2-point function in k-space. K1, K2 was a delta function. With the power spectrum, well, the bispectrum, what you get is the bispectrum amplitude and a delta function which says that the 3 k vectors have to make a triangle in k-space. They have to close up. So somewhere in k-space you have K1, K2, K3 going around a triangle. And the result, of course, now is sensitive to the shape of the triangle. But that's important because what we saw was that the galaxy distribution tends to become very filamentary, nodes connected by filamentary material between them. So that means if you carry out a three-point analysis, the result of that three-point analysis should be sensitive to triangles that are very flattened in that sense. They'll have a larger amplitude that will pick out the filamentary signal. And that's a way of splitting the degeneracy that would exist perfectly in the regime of linear theory between the amplitude of the matter fluctuations and the degree of bias. And this was carried out with 2DF with a very nice paper by Licciarverdi. And basically this plot here is a function of k going, 0.1 to 0.5, shows you the bispectrum amplitude for equilateral triangles and rather flattened triangles. And you can see that there's a characteristic difference in shape, and that shape is as predicted according to perturbation theory. So there's an example. Generally, everything I'm talking about is at the two-point level, but there are times, particularly here, where we're looking at the correlators at a higher level is very important. All right, back to the two-point world, though. The previous talk, I discussed the concept of local bias, just the idea that the galaxy number density was some complicated function of the local matter density. And I showed you, or I told you, and motivated it by an example, that that's something that should be monotonic with scale. And that caused a lot of puzzlement about 20 years ago, because by then the M-body simulations were pretty good. And so we could measure, so here is as a function of redshift, going from redshift 1 up to redshift 0, these curved lines are the predicted matter correlation functions for the CDM model, and they're contrasted with galaxy data, which, as you can see it more clearly here, is basically very close to a power law correlation over 1, 2, 3.5 powers of 10. So if you take the ratio of those two and take the square root, I just rubbed the equation off, but the square root of the ratio of these power spectra should give you a scale-dependent bias. And you can see that this is at redshift 0. It's non-monotonic. It has this strange curved shape. So this represented a challenge because there are other reasons for liking Lambda CDM. So why wasn't it able to account for biased galaxy clustering? Here, by the way, is a model with a matter density of 1 and a lower normalization. And you can see that over a wider range of scales, the bias is pretty well constant. So this is extra evidence that even in 1998, people were still thinking quite hard about this Einstein de Sitter universe as the solution. In retrospect, the reason why this didn't work out is obvious. We need a non-local model for bias. It was clear all the time that there should be one. And this is a piece of standard technology in the field now called the halo model. So let me take you through it. Like all the good ideas in cosmology, it's very old. It goes back to the 1950s. In fact, it goes back beyond that. We like to think in astronomy that we're kind of pure scientists. We don't work for the military and do harm to the planet and so on. But Nyman and Scott, famous statisticians, they were employed during the Second World War to answer this question. If I have a beach full of troops and I want to kill as many of them as possible, where should I put my shells? And so they worked on a Poisson model where you just randomly throw shells onto the beach and figure out how many troops you kill. And this has now given us a standard tool in cosmology. So after the war was over, they started thinking about whether this could account for galaxy clustering. And they said, well, supposing I do this in 3 dimensions, I throw down a number of clumps, each of which contains some number of galaxies. This will produce a correlated density field because a galaxy in a given clump tends to have a neighbor within that clump. And if you assume that the clumps have a power law density distribution within them, it's easy to show that you get a power law correlation function, and everything just depends on the on the slope of the index. And so you could match the observed power law slope of galaxy correlations with a density to the minus 2.4. And there this sat doing nothing for half a century until we realized, belatedly, much later than we should have done, that all the techniques needed to put this into CDM were in place. And so this occurred to a number of people just around the turn of the century. So here's what we do. Let's start by shelling the enemy. We'll distribute dark matter halos, because the dark matter halos are the modern equivalent of the Shane-Neumann clumps. We'll put them at random throughout the universe. We know what the power spectrum of that is. It's shot noise, governed by the number density of the halos. But it's not pure shot noise, because these shots have a finite size. So having put this power law power spectrum down, we will then convolve it, or convolve the density field, and therefore filter away the high K power. Here, I hope we're just taking rho equals some Poisson point process convolved with, I shouldn't call this rho, convolved with the profile. So it means that the power spectrum is filtered by some window that's set by the finite size of the halos. We know that in cold dark matter, halos come not just at one mass, they have a variety, so you need to know the mass function. So f of m dm is the number density of halos sitting in that mass range dm. And once you've finished doing that model, you then realize that it was stupid to put the halos down at random, because we know there is large-scale clustering. So it's completely natural to take the halo centers and displace them. Because remember, you can view the density field as a result, as I said before, density fluctuation is minus the divergence of a displacement. So this displacement moves the halos. And as a result, the overall power spectrum has a contribution at large scales, which is just from that displacement, the linear power, adding to a small scale power, which is basically just a filtered form of shot noise. This model isn't perfect by any means, not least you'll notice from this sketch the idea that there's nothing to prevent halos overlapping. So in practice, you can deal with this if you actually take halo catalogs that are generated from n-body simulations and calculate the power spectrum from their mass profiles. Okay, so what do we know about the mass profiles of CDM halos? Well, how do we find halos? We are motivated by the spherical model. So we heard that there you expect an object to settle down so that its boundary is such that the average density within it is about 200 times the background. So that means there's an easy way of searching for halos, which is you just need to find clumps of dark matter particles in a simulation that satisfy that density criterion. And the neatest algorithm is called friends of friends. And you just pair particles within a distance about 0.2 times number density to the minus 1/3. So if you take 1 over the cube of that, you'll get about 200 times the mean density. And so you find groups of particles that are all connected in that sense. And that gives you a catalogue of halos. You can fit density profiles to those, and mostly these come out looking somewhat similar to the well-known case of the isothermal sphere. So this is a beautiful test example of an object that's held up purely by the dispersion of the orbital velocities within it. And it has a density that goes as 1 over the square of the density from the center, 1 over the square of the distance from the center. So people tend to talk about, well, the NFW form showed really that the slope, so rho versus r, isothermal halo would be something like that. Real halos, if you can use the term real for something that only exists in an n-body simulation, tend to have profiles that are curved like this, flatter than isothermal in the center, steeper at the outside. So we know what they are. We can calculate their Fourier transform, use it in the halo model. You need the halo mass function. Again, this was mentioned earlier. This started life in 1974 with Preston-Schechter's argument, which is actually beautifully simple, and again based on the whole idea of thresholding motivated by the spherical model. So the idea is you think of a mass that you're interested in, and you say that mass is associated with the mean density of the universe times the radius of some sphere. So you're basically taking the density field, convolving it with this sphere, and asking what the variance of that convolved field is. That gives you some Gaussian process. And then you ask, what fraction of space exceeds the threshold for collapse, delta C? The trouble is, half of space lives below the mean density, so it can never collapse, apparently. And Preston-Schechter just said, okay, so we'll put in a factor 2 times the collapse fraction, which is that shaded area is the fraction that's deemed to collapse. It turns out that argument doesn't match n-body simulations. Again, you can find fitting formula that look similar that do a better job. So here's how the mass function would evolve. Let's say it's got 2 powers of the mass times the mass function. So actually, if you think about it, that shows you the fraction of the density of the universe that's carried in a given log mass bin. So you can see that today, the mass bin around 10 to the 14 solar masses is what dominates at redshift 5. That would have been down below 1 billion solar masses. And it just increases hierarchically with time. But at any redshift, we know what it is. So we have all the ingredients needed to calculate nonlinear correlations by the superposition. And here's the result, broken down by the contribution by different halo masses. So here's the one halo term, these open circles. So it's in the form of pure shot noise at large scales. On small scales, it falls over. And that's just the finite size of the halos. And that contribution, it falls over on large scales, big halos, 10 to 15 solar masses. For small halos, say 10 to the 10, it carries on more of this shot noise to very small scales. And that's why you get a very slow, broad curvature. You add in linear theory, there it is, and you get the overall black prediction, which has this nice inflection in it. Which actually, let me skip ahead, has been seen. So this was probably the first great achievement of the Sloan Digital Sky Survey, was to show that if you ratioed the galaxy correlation function to a power law, you got an inflection which is fitted naturally by the prediction of the halo model. So it was at this point that people became convinced that this was a good way of thinking about the universe. But I've skipped over something important, which is the relation between this, which is the halo model prediction for the whole mass field, and galaxies. So we need to think about galaxies. And the reason this is a fruitful approach for galaxies, and understanding that galaxies of different kinds can have different degrees of bias, is because the amplitude of bias depends on the mass of the halos. So if different galaxies live in halos of different masses, they will automatically be more strongly correlated. So this shouldn't surprise you. If you just look back at the original analysis from Kaiser in '84, what did he say? He said that the rarer a density excursion is, the more strongly biased it's going to be. So of course, extremely high mass halos are very rare objects. There's almost nothing in the universe today with a virial mass of more than a few times 10 to 15 solar masses. Right? So those objects automatically will be extraordinarily strongly biased. So let's just see how this works out in the context of Press-Schechter. And it's this the same argument that we heard earlier, the peak background split. Just imagine the density field decomposed into a small-scale halo-sized component and a long wavelength swell underlying it. What you do is simply say the effect of this long wavelength disturbance is just to perturb the collapse threshold in the Press-Schechter formalism. It means you replace this delta C, this 1.686 magic number, with something that's slightly different. The halo mass function responds, well, it analytically knows about the value of the collapse threshold, and it responds linearly to this linear perturbation according to its derivative, so you can easily compute Lagrangian bias, that is, how many more halos a given Lagrangian region of space will get. And then you do the Lagrangian to Eulerian transition of adding 1, and you get a prediction for the total bias parameter. And it depends just on the mass through this variable nu, which is delta C divided by sigma as a function of r, which is this thing, but as we saw, that's also as a function of mass. Analytically, in the Press-Schechter formalism, it looks like this. So what you see is that nu equals 1 halos, which are the kind of typical halos in the mass function, are expected to be unbiased. So B versus M over M star. M star would be the kind of exponential cutoff point in the mass function. You have something a bit like this, and it says that low mass halos, so galaxies, dwarf galaxies that inhabit unusually low mass halos, would be expected to be anti-biased. And that can go down to 1 minus 1 over 1.686, so whatever that is, 6 or something. Okay, so it's quite possible for galaxies not only to be more strongly biased than the mass, but also less biased. And this general relation between the mass function and the degree of bias was pointed out in a beautiful paper by Sheth and Torman. So it's a shame that Ravi isn't here so that we could say thank you to him for that nice insight. Okay, so we're almost there. We just need the last piece, which is what I call the occupation numbers of the halos. You've got to understand as a function of the halo mass how many galaxies you're going to insert into each halo. And it's easy enough to argue that once you've picked, let's say you pick a given category of galaxy, you have to decide, I'm going to work with a catalogue of galaxies whose stellar mass exceeds twice the mass of the Milky Way. I don't know, any number that you are observationally interested in, then it's fairly clear that for low enough halo masses, be sufficient baryons in that halo to make even one galaxy of that stellar mass. As you rise, you'll reach the point where maybe it's possible to make one, which will be a central galaxy in that satellite, in that halo. And as you go to higher mass still, you'll have some mass left over, which will go into satellite galaxies. So the very simplest sort of occupation curve that you could imagine would be a one-parameter function, and it would look like it would look like this. So you turn on your central M1, and M2 could be another parameter, but often this is like M10 times M1, so you could fix that, and then this rises proportional to M. So with that fixed shape, the only free parameter would be the turn-on mass. But actually, free, because if you change the turn-on mass, you'll change the number density of the galaxies, because the number density of halos is given by the cosmological model. So this actually gives quite a well-constrained way of even predicting what halo bias should be. So here's a general expression for it. It's the +1 from the Lagrangian to Eulerian transition, and then you have halo bias as a function of mass, weighted in some way as a function of halo mass according to the occupation number that you put in. And as soon as you've decided that, the bias is predicted. So in principle, you're going to either take the observed level of clustering, predict the number density, or vice versa. And if those don't agree, you can go to a more complicated halo occupation number. So here is the results of doing this for the Sloan data. This is probably not easily visible, but basically it goes from black lines. These are R-band absolute magnitudes, if that means anything to you, but dwarf galaxy level, Magellanic cloud sort of systems is down here. No, sorry, other way, down here. And the most luminous galaxies, kind of central galaxies of rich clusters, are at this sort of level. So the shape needs to change in detail if you want to match the abundance and the clustering data. But when you've done that, then it's quite impressive what's achieved. No. Okay, what's shown here is something I'm leaving for tomorrow's discussion, which is the results from clustering in redshift space. But if you know what that is, you can, this is the monopole and the quadrupole, which tells you something about how clustering depends not only on the amplitude of, or the separation of a pair, but also whether it's orientated transversely to the line of sight or radially. So we'll talk more about the anisotropy here, but the point is it's predicted really very impressively by this model. So the halo model works, and even better, it's useful, because something that we increasingly need to do in modern large surveys is make ensembles of fake data sets. We need to do that to push them entirely through the analysis pipeline so that we, A, can be convinced that we can recover cosmological parameters in an unbiased way, but B, we can put realistic error bars on them. And there's no better way of doing that than just brute force analyzing an ensemble of simulations that has a proper cosmic variance imprinted on it. So the idea would be that you run an n-body simulation, you extract from it a catalogue of dark matter halos, you populate them according to this recipe, and it gives you many fake Sloans. So this is a technique that has a lot of computational time invested in it at the moment. Yeah. I'm sorry, I couldn't. Yes, that's right. Well, it's all that's happened here is that the idea that there could be a Heaviside function turn on is obviously unrealistic. So what this is saying is some, at 20 minus 21.5 at 10 to the 13 solar masses, most of those halos don't have any galaxies in at all. Right? So what you would do is just say it's 20%. So you would randomly pick 20% of those halos, allocate them one galaxy. And but there's no reason why you shouldn't soften this transition, and the softening has to be quite extreme here to fit the data. But it's a question of whether you're impressed by how many data points you can fit when you think, the number of free parameters in this is probably 1 for the turn on, 2 for the degree to which it's softened, 3 to where the satellites start to come in, and possibly 4 for the slope. So 4 parameters allows you to fit all of this. I think it's pretty good. All right. So the halo model is also a good way of understanding some of the limitations to the precision of these cosmological measurements if we're going to go into the nonlinear regime. Because I gave you the argument of cosmic variance in the linear regime, it's just mode counting and based on the fluctuations in the Gaussian field. So at small scales, things are non-Gaussian. What do we do? Well, in the halo model, it's relatively easy to see how this is going to work out, because the overall power is a sum of 2 components, one of which is the linear power spectrum, which obeys Gaussian statistics, so its fluctuations are predicted with no changes needed to the machinery you already have. Just the fractional error is going to be set by the reciprocal square root of the number of modes available, which is survey volume over 4 pi squared k cubed times the bin size in log k, all to the -1/2. So we know how to calculate the statistical fluctuations on this. And to that, we're adding the one halo term, which is basically, as I said, in the form of shot noise. You could also say that there will be additional shot noise based on the number of galaxies. But typically, although not always, there'll be many more galaxies than halos. So let's neglect that for now. So we're then just asking, well, what's the statistical fluctuations on shot noise? But that's really easy, because the amplitude of the shot noise is just set by the overall number of halos that you have. So if that's and if you have a Poisson process, then you know what the variance in the Poisson process is. It's just set by the number of objects. So you have a very nice prescription for the variance in the power, which is 1 over the number of the modes from the cosmic variance in the linear 2 halo term, plus 1 over the number of halos in the 1 halo term. And so if you re-express the number of halos in terms of the shot noise amplitude of the small-scale power spectrum, you can write it like this. So basically, it's the power you get, the variance, fractional variance in the power even, is what you would have written down in the Gaussian regime with a correction factor that rises with this form. It's proportional to the power and to the bin width in K at small scales. And here's what you actually get out of ensembles of simulations measuring fluctuations in power. It sits at the Gaussian level, and then when things go nonlinear, in this case it was 0.4, 0.5, you see this additional kick up, and it's predicted nicely by the halo model. So to some extent, you can see that when the one halo term starts to become dominant, you more or less reach the limit of useful cosmological information. But we can understand why these additional small-scale errors in the power exist and what their amplitude is. Okay, I know. Okay. They didn't start the timer, but I don't want to take all my time because I know it's late and your brains are probably even more fried than mine is. I hardly slept at all last night. I hope you're not all suffering from jet lag the same way. But just a few more nice properties of the halo model. One thing is it includes naturally something that people mused about, again, at the turn of the century, which is called stochastic bias. There was a concern that all the discussions of bias, particularly the local bias model, was that the galaxy density fluctuation, that's what little g stands for, was just basically some nonlinear function of the matter density. But was that function causal, or could there be some dispersion about it, some additional fluctuation epsilon? Well, the answer is yes, we expect that there will be such a fluctuation just because of the finite number of halos. So if you measure this relation, and to do so, because galaxies are a point process, you've got to impose some smoothing. So let's do this at around the nonlinear scales of interest, spheres of 8 megaparsecs. Just smooth with an 8 megaparsec sphere, measure the amount of mass inside that sphere, measure the number of galaxies, and plot the fluctuation one against another. So what was done in this particular exercise was counting halos of this is 10 to the 2 times 10 to the 13 solar masses, 2 times 10 to the 12. The exact figures don't matter. The point is there's a complicated nonlinear relation between the number density of halos and the matter fluctuation, and there's a dispersion. That's fine, because that dispersion is something that's predicted naturally within the halo model. So it's not like there's an additional source of uncertainty in galaxy clustering. This is something that's automatically built in. While we're talking about this, by the way, we've reached the point now where, right at the start of the first lecture, I talked about the Poisson clustering model, and I said it was only approximate, and now we can see why. So we said that shot noise was a kind of discreteness correction, but that doesn't mean that the galaxies have to be placed randomly. So in the halo model, one galaxy is always placed at the center of each halo. And if you had a particular population, and you can try and optimize selection constraints based on the galaxy colors and luminosities to identify predominantly central galaxies, suppose you succeeded perfectly in this, then each galaxy would mark one halo. And so what would the 2-point correlation function of galaxies tell you? It would tell you the 2-point correlation function of the halos, that is, of the mass. Because the small-scale correlations of halos in the halo model are shot noise. So in this case, you absolutely wouldn't want to subtract the shot noise from the galaxy correlations. Otherwise, all the signal would go away. So really, the Poisson clustering model and the subtraction of the shot noise only makes sense, really, if you're talking about a galaxy population that's satellite-dominated, with many more satellites than centrals. Okay, so the real question for asking whether the halo model is a good way of implementing galaxy clustering is to ask whether, even though there are fluctuations in the number of halos in a given volume, are there fluctuations in the galaxy contents per halo? Because that's not built into the halo model. At the moment, it's assumed that once you know the halo mass, you know precisely what the galaxy contents will be. And we need to worry if that assumption is true. How can we test it? Well, one way we can test it is by looking, obviously we don't have access directly to the dark matter field, but we can look at different kinds of galaxies. So this is the whole area of multi-tracer cosmology. So here's a kind of cartoon. It looks like a cartoon, but colossal amounts of CPU time are actually invested in running this simulation and then running a galaxy formation code to predict colors and stellar masses of galaxies within it. But it does look like a child's painting, nevertheless. The point is, you can see the red galaxies, the ones with old stars, are indeed more clustered, more concentrated in high-density regions. So let's compare how those old and young populations fluctuate with each other. And this is something we did with 2DF. Again, Vivian Wild led this paper. Split the universe up into cells, split the galaxy population. In this case, we did it by color, red and blue. So basically old stellar populations, young star forming. And in each cell, you can calculate a density fluctuation. And you can plot them against each other. So, yeah, so this is the data. So this is red density against blue density on a log scale. And you can see, well, the best fitting line has a slope that isn't unity, so there's some kind of parallel or bias between these two. On the other hand, and there's a scatter about that line as well. So the real question is that scatter consistent with shot noise? That is, apart from the finite numbers of galaxies per halo, is there any indication that the scatter between red and blue numbers is non-zero? We concluded that it was, actually, that there was a correlation coefficient of about 0.97. So at the few percent level, there was some non-universality in the mapping between halo mass and galaxies of a particular type. But that signal is completely insignificant for any measurements that we needed to be interested in. Yeah. That is because of the selection function. In order to, obviously down here, things are discrete because in a given cell you have one galaxy, two, etc. But you don't convert that to a universal density contrast because we're covering a range of redshifts. Okay, so the sampling of the survey wasn't completely uniform, and so you have to make a correction for the fraction of missing redshift in a given cell, and that turns it changes the effective volume of the cell, if you like, into a slightly varying number. But well, I think you're asking about whether it matters where the cells are placed. Oops, sorry, wrong way. And it shouldn't do, as long as they're placed without reference to the galaxy density fluctuations. I have to say, we didn't try doing this with more than one geometry. We just picked one at random and then used it. Yes. Anyway, so right. So that was stochastic bias. To a good approximation, it's not something to worry about, and so therefore the halo model really is doing a good job in delivering predictions for a multivariate distribution of galaxies. It's widely used. So just to finish, what are its deficiencies? Because people want to keep probing this and see if we can do better, of course. And something you'll hear a lot about, if you're interested in the subject at all, is assembly bias. So I wanted to have a little rant about this, because I think a lot of what's written in the literature is wrong or misleading. People will tell you that assembly bias means that if you take a set of dark matter halos, all of which have the same mass, and let's say we do this today, you can ask the question, when did those halos form? Because they were assembled by hierarchical merging. So you can ask a question of how far back in time do I have to go before, let's say, there was a single halo with at least 50% of the mass of the object I'm interested in today. Whether it's 50% or some other number doesn't matter. You can define some point at which that object was first assembled out of putting together smaller fragments. And that number varies stochastically. Different halos have different formation redshifts. And you will read statements saying that, well, the halos that collapse earlier are more clustered, and this is not included in the halo model. Okay, well, that's just plain wrong. I showed you in the first lecture that this effect is exactly what Kaiser 1984 was all about. Rarer fluctuations, that is ones that collapse at higher and higher redshifts for a given smoothing scale, are more correlated. That's precisely what Kaiser's bias expression was telling you. We don't see this in the halo model normally, because when we report a bias for halos of a given mass, we're automatically averaging over formation redshift. Right? So let's say we take halos that have a bias that depends both on their mass and on their formation redshift. And we put into them a halo occupation number, which depends only on mass, which is what's normally done in the halo model. Now average over formation redshift. What is the typical bias of the galaxies that you've made? Well, you take the bias, you multiply by the number of objects you've got, and you average it over Z formation. But because the bias is the only thing that depends on the formation redshift, that multiplication, the average of that multiplication factorizes into the mean bias times the mean number. And so when you read in the halo model, the bias of halos of a given mass is this. It's this quantity that's discussed. It doesn't assume that there's no dependence on formation redshift. And so now you can see that assembly bias is an issue that one needs to worry about, because if you take a halo of a given mass and form it at a higher redshift, you might well think that the galaxy population would be different. If you form it early, you've got more time, the stars will be older by the time you get to the present. If an object of a given mass forms at a higher redshift, it's denser, it's a deeper gravitational potential well, it actually means it's harder for feedback effects to quench star formation. So star formation could be continuing today in such an object, whereas one that formed more recently, feedback could have quenched the star formation process. So there's plenty of reasons physically why there could be a dependence of galaxy contents. So then, fine, if you take a bias that depends on mass and formation redshift and contents that depend on mass and formation redshift, then sure, the mean galaxy bias doesn't factorize in the way that the simple halo model predicts. Right? But that's nothing to do with the fact that early collapsing halos are more strongly correlated. Right? It's two completely different things. Okay, that's my rant over. I want to stop soon because we used up a lot of time today. Let me just have one last slide. So there's some indication that this sort of thing is going on, and it's under the heading of what's called galactic conformity. And that says that actually the dark matter halos, the galaxies within them know something about other galaxies. So this is a plot that shows you the fraction of late type galaxies, that is star forming galaxies, as a function of halo mass. And it's showing you split into two kinds of halos at a given mass. So you can see that there are some with a higher fraction of star forming galaxies than others. And what's the difference? They're split according to the star formation rate of the central galaxy. Okay, so at least the satellite galaxies within a halo know about the star-forming type of the central galaxy. So if you wanted to construct a halo model where you simply said the central galaxy is either red or blue, and now I will just randomly put in red and blue satellites, that's clearly inconsistent with the data at the level that we can measure. So if we want to make realistic simulations of galaxy clustering to test out future survey analyses, these sort of effects are going to have to be measured more precisely and included. All right, I think that's probably a good place to stop. You may have enough energy left for questions, I don't know, but anyway, there's always tomorrow. Thank you. Okay, thanks.